Right, change my pen for question 2. Let's see if this is less shiny. Car of mass 600 kilos starts from rest and moves along a straight horizontal road. At time t seconds, the force acting on the car has a magnitude given by that expression, acting in the direction of motion. Resistance to motion may be ignored. Find an expression for v, the velocity of the car at times t. Hence show that the speed of the car has a limiting value as t increases, and find this limiting value. So this one's a bit trickier to spot that it's actually a differential equation. With the first question, we were given that the dv/dt expression that we were aiming for. So it's a little bit more challenging here to actually spot that it is a differential equation question. So let's set it up. Diagram, car, and what do we know? We know it's got a mass of 600 kilos. At times t, the force acting on the car has a magnitude of 27,000. So if this is my direction of motion, this is the way that it's accelerating. This time we can ignore resistances, and this is what's driving it forward. Okay, it starts from rest, so we know that when t equals 0, that's what I was looking for then, v equals 0, so that will allow us to work out the constant of integration. And it's not telling us that it's moving in a constant velocity or constant acceleration, and in fact, because it's given in that form, we know that it's not, because as t varies, that force is going to vary as well. It's also going to be always positive because the variable is t, which is always going to increase. So using Newton's second law, my force is 27,000 over t plus 3 all squared equals the mass, which is 600A. Now I know that the acceleration is the rate of change of velocity, so that's going to bring my v into it. So now I'm going to have 600 dv/dt equals 27,000 t plus 3 all squared. If I divide throughout by 600, gives me 45. So dv/dt is 45 over t plus 3 all squared. Now I need to solve that by separating the variables. So I'm going to have dv on its own on that side, and on this side 45 t plus 3 all squared dt. Oh, still reflected. Let's switch my light off. Bear with me a sec. What about that? That's better actually, isn't it? Okay, I'll persevere with that. Right, so that's straightforward to differentiate. This one, it's not a natural log because it's to a power, so that's going to be dv, and I can write this, take the 45 out, it's not going to add anything to the integral, so I've written that now as t plus 3 to the power of minus 2 dt. So it's a straightforward one to integrate. This side I'm going to have v, this side I'm going to have 45, and I'll just leave that there for a moment. I'm going to add 1 to the power, so it'll be minus 1. So it'll be t plus 3 to the minus 1 over minus 1, and then I'd have to multiply that by the differential of the inside, which is just 1, so that's straightforward, plus c. So just to untangle the knot that we've got there, I can write that as that. So make sure that you're happy with what I've done there. So I brought the t+3 back underneath by dealing with the -1 index, and then I've written it as -45. I need to deal with the constant of integration, and I know that when t is 0, v equals 0. So we're going to have 0 equals -45 over 3 plus c. 45 over 3 is 15. So c equals 15. So v equals 15 minus 45 over t plus 3. What else do we got to do? So I found an expression for v, hence show that the speed of the car has a limiting value as t increases, and find this limiting value. So the variable here is t, and what's going to happen is as t gets bigger and bigger and bigger and bigger, this is going to get closer and closer to 0, because you're going to end up, let's say after 1,000 seconds, that's going to be 45 divided by 1,003, which is going to be 0 point something. After 10,000 seconds, it will be smaller and smaller. So as t increases, that tends to 0, so the velocity is going to tend to a maximum value of 15. So as t tends to infinity, 45 over t plus 3 tends to 0, and therefore the velocity tends to 15 meters per second. So that's a pure maths thing there about limiting values. So find an expression for v, done. Hence show that the speed of the car is a limiting value, done. Find this limiting value, done, it's 15. Calculate the distance travelled by the car in the first 6 seconds of motion. Give your answer correct to 2 decimal places. Okay, so part B. So I've now got an expression for v, which is 15 minus 45 over t plus 3. So I've finished now with the differential equations. What I'm doing here is the variable acceleration maths, where that I know that distance is rate of change of velocity. So now v is ds or dx, whichever one you want to use, dt. So I've got dx dt equals 15 minus 45 t plus 3. Separate my variables. Dx on this side, and on this side 15 minus 45 t plus 3 dt. This becomes x, and this side becomes 15 minus 45 ln of t plus 3 plus c. So that's just, if you took out the 45, it would be 1 over t plus 3, which is just ln of t plus 3. Then I need to get rid of the constant, and I know that when t equals 0, x equals 0. It starts from rest and moves along a straight horizontal road. So this is going to be 0 equals 15 minus 45 ln 3 plus c. So c will be 45 ln 3 minus 15. No, it won't, because that's 15t. When I integrate that, I get 15t. My bad. So that's gone, and that's gone, and c is 45 natural log 3. So therefore x equals 15t minus 45 ln, and I don't need the modulus because t is positive, so I can just write that as a bracket, and then my c is 45 ln 3. And I want to find the distance travelled in the first 6 seconds. So when t equals 6, x equals 15 lots of 6 minus 45 natural log of 6 plus 3 is 9 plus 45 ln 3. So 15 times 6 minus 45 natural log 9 plus 45 natural log 3 equals 40.56 meters. So one little slip from me there. When I integrate a constant, I introduce a variable. So yeah, so that's question 2. Just go and upload that for you now.